Okay, last time we talked about algebraic optimization, and I argued that all three of these expressions, without going into a lot of detail, but I argued that all three of these were equivalent, and they differed only in the order in which things were evaluated. Here you evaluate this join first and this join second, and in this expression you evaluate this join first and this join second, and here you sort of find all possible combinations of tuples and then filter that. And so if you don't understand exactly what's going on in these expressions, that's okay. You're not going to know that we'll talk about it. In fact, in this segment, I think. But the takeaway here is that there's three equivalent expressions, and we don't know necessarily which one is the fastest one to evaluate. But the database can figure this out and does every time you write a query. Okay, and that's this notion of algebraic optimization. Now, we don't, even if you're familiar with databases, you may or may not be familiar with the relational algebra. Which should be strange because I've argued that it's the hallmark of databases and totally fundamental. So why don't we think about programming databases in terms of writing relational algebra expressions? Well, another good idea, another key idea that's associated with relational databases is this notion of declarative languages. And what we mean by declarative languages is that you specify the answer that you want, but you do not specify anything about how to get it. And so a relational algebra expression actually does specify an order, right? As I showed on this slide, here's three different expressions that's indicating exactly which order to do every operation. That means that if you write an expression like this, you're instructing the computer, look, do it in this particular order. Okay. And so these declarative languages say, look, we're just going to describe the properties that must be true of the result, and we're going to let the database figure out the right order in which to do this. And so here's a quick example. So imagine you have two tables. One is order with 3 columns, order, date, and account, and another table with item with 2 columns, order and part. And the semantics here is that this column indicates which order that item should be associated with. Okay. And so if you want to say find all orders from today along with the items ordered, then you might write this query. And if you've seen SQL plenty of times before, bear with me, and if you haven't, then pay attention. So select star, give me all possible columns from the table order and all possible columns from the table item. But I only want records such that this condition is true, where the order column from the order table matches the order column from the item table, right? And then further, I only want orders from today, where order.date equals today. So this is just conditions expressed over the result without any kind of idea of how to actually get this answer. So what automatically happens is that this query is translated into a relational algebra expression along the lines of what we've already seen. Here I've sort of just done a cartoon where you can say scan the item table, scan the order table, select the records such that date equals today, and then perform the join, find all the records in order that correspond to for each record in order, find the corresponding records in item that match on order. Okay? So this is happening every time you run a query again. So the SQL is the what, not the how. Given another example, there's 3 columns, product, purchase, and customer. And the underlining here we haven't talked about, but this is the indicating what makes the table, what makes each record unique. And so here the PID makes the product unique, the CID makes the customer unique, and the combination of PID and CID makes the purchase unique. Okay, so here's another SQL query. We say select distinct product name. Why do I know it's the product name? Because I see an X here and I see an X here. And the customer name, and I know it's the customer name because I see a Z here and I see a Z here. This is an alias for the relation customer. From these three tables, where the product ID in the product table matches the product ID in the purchase table, and the customer ID in the purchase table matches the customer ID in the customer table. And that's a typo, it looks like. That should be Z. So maybe change that on your own slides. Yeah, let me see if I can fix it now. Z.CID. And then but now we want only the products for which the price is greater than 100, and we only want the customers whose city is Seattle. All right, so what does this say in English? Well, find me combinations of products and customers, unique combinations of products and customers where the customer is in Seattle and they paid for a product worth more than 100. Okay, so it's clear what we want, but it's unclear how to get it. It's kind of a complicated query. Okay. So translating this into relational algebra, we have this. So at the bottom we have product and purchase, and now we do this join where we say, for every product, find me the corresponding records in purchase. Then we do another join. For every record in the result of this join, find me the corresponding records in customer, right? Now filter out all those records such that where price is not greater than 100. We only want the ones where price is greater than 100, and we only want the ones where city equals Seattle. And then we want to, in this case, project down onto these two columns. What I mean by project is get rid of all the other columns except for the two we're interested in. Okay, and then finally take the final answer. So the 2 points here is that the execution order is now clearly specified, but there are a lot of physical details are still left open. You know, this is a very high-level indication of what's going on. Order of operations is clear, but that's about it. We don't know how we're going to do the join exactly, and there's multiple ways you can do it. I've indicated that, you know, we're going to take for every record in product, we're going to look up a corresponding record in purchase, but we haven't said precisely what that means. Okay. I'll give an example of this in a second. So another example here. Here we only have a single relation called R, and it's got 3 columns: subject, predicate, and object. And you see this kind of schema when you hear about when you work with RDF data, the Resource Description Framework. Right? And RDF is a language and formalism and software stack for managing what is called linked data. And here, sort of everything is, it's a set of all facts. You can, any kind of fact you can come up with, you can encode in RDF. You can say, you know, the instructor of this course is Bill Howe, right? So here the subject might be this course, the predicate is has instructor, and the object is Bill Howe. Okay, and so this is people use this formalism as a very general way of encoding any information from any source, and we might touch on this much later in the course. Okay, and so here's kind of a complicated query, but what it says is I'm going to have 3 instances of the same relation, and I'm going to join them all up, and I'm going to look for a sequence of tuples such that we have a person who knows another person who holds the account of a company who has an account homepage of a particular value. Right? So you're looking for this sequence of where this edge is knows, and this edge is holds account, and this edge is account homepage. All right. So find me all possible combinations in this table where I've got, you know, find me all A, B, all instantiations of A, B, C, and D such that this pattern matches. Okay, and the joins are specified by these conditions. The object of the first relation must be equal to the subject of the second relation, and the object of the second relation must be the subject of the third relation. Okay, so I'm looking for patterns in the graph that look like this. And in relational algebra, you see this query gets translated into this form. There's a selection to find predicate equals knows. There's a selection to find predicate equals holds account, and there's a selection to find predicate equals account homepage. And then you join, and then a sequence of joins, And finally, a projection just to pull out the final answer that we're interested in, which is the select clause. Okay, so perhaps a kind of complicated example, but I think the takeaways here, I wanted to mention RDF because we might come across it again. And I also want to demonstrate that you can access the same relation more than one time in a single query. And then I wanted to give another example of translating even complicated queries into relational algebra expressions. Okay.